Hi. Given the time, I decided that we'll do a little bit of a fun topic, the game theory of the coronavirus. So I'll start on the first game, which is what I call the toilet paper game. The idea is you need toilet paper, and you can either buy a small amount or a large amount. And you have a neighbor that has to make the same decision. The store has only a limited supply. And if the store is out and you go to the store and you try to buy some toilet paper, it's a major pain in the butt for you, so to speak. It's less convenient to have a large supply at home because you need to store it somewhere. But if everyone just buys a small supply, it'll be enough for everyone, and there won't be much of a problem. If everyone tries to buy a large amount, some will get it and others won't be able to get it. So let's look at this game. So the idea here is that there's you and your neighbor. If you both buy a small amount, you each get utility 5. If you buy a large amount and your neighbor buys a small amount, well, you're going to get your large amount. And you'll get utility 4, and it's less than 5 because it's a pain to store a bunch of toilet paper. Now, your neighbor gets -2 because he'll get a small amount now, but next time he goes to the store, chances are it'll be empty because you've bought up everything. Now, if you both buy a large amount, then there's some chance it's better than buying a small amount because there's some chance you'll actually get the large amount, but there's also a chance that you wind up not being able to have toilet paper. So if we look here, you can see that there's 2 pure strategy Nash equilibria. One, which is probably obvious, it's the 5-5 one. And that's because if you both choose a small amount, there's no incentive for you to deviate to 4. So if you switch from small amount to a large amount, you get 4 instead of 5. So you stick with small. And it's the same for your neighbor. If he chooses a large amount, he gets 4. He'll rather stick with a small amount. Now notice there's another Nash equilibrium, which is a bit less obvious. And that's 0-0. So that's if you both choose a large amount, then again, actually, neither of you has incentive to deviate. That is, if your neighbor's choosing a large amount, then you don't have an incentive to switch to a small amount because next period you'll wind up with not having enough. So we see that there's 2 pure strategy Nash equilibria. There's also a mixed strategy Nash equilibria where you sometimes buy a small amount and sometimes buy a large amount. But we won't get into that right now. So now this game with these 2 Nash equilibria, notice it's simplified, but a sequential game where you go to the store in several periods, well, that's going to be a very similar effect. So the fact that you choose simultaneously doesn't really distort the actual game. So that's one thing that's interesting. And notice that what are some of the possible solutions is, well, one solution is rationing. What you want to do is you might want to ration the amount of toilet paper you want to have. It might be slightly inconvenient because sometimes you might actually want to have large amounts of toilet paper, but it also might not be fully effective in that it might just stop people from going to one store, but rationing, people might just go to several stores and buy large amounts by buying small amounts in each of the stores. Now, something my brother said when I mentioned this game to him is he said, well, look, actually, in certain cases, it is convenient for me to buy a large amount. in that especially now I have to do less shopping trips, and that's a distinct advantage. But notice overall, this game is what we call a bank run, very similar to a bank run, which we discussed in class earlier, where withdrawing cash early is very similar to hoarding toilet paper. And in that case, you see banks might want to limit the amount that each person can withdraw. But one of the key things to take away from this is that even though it seems crazy that people would go to this equilibrium of a large amount and large amount, it is an equilibrium that everyone tries to buy a large amount of toilet paper. As crazy as it seems, because why wouldn't people just buy small amounts? If everyone buys small amounts, it won't run out. And I guess also the hoarding is, it really would only apply to goods that you can store. So like fresh vegetables, fresh meat, fresh fish. Well, I guess meat you can put in the freezer, but generally those that would expire fairly quickly, milk products, then those are less likely to be hoarded. And quite ironically, in some sense, that those are going to be in supply, when actually ones that should be less problematic, like toilet paper, actually will have problems or potentially have problems. So this is one sort of game theory of the coronavirus, which might seem a bit strange to you because everyone's puzzled, why are people buying toilet paper? And the bottom line is, the only reason why people were hoarding toilet paper is because other people were hoarding toilet paper. So now I'd like to talk about a different type of game. That's the social distance game. And that's, you have to decide to go to an event, like a tutorial, a restaurant, movie, even going to work. And you want to go, generally, to these things. But everyone going, it decreases the social distance and increases the risk of spreading and catching the virus. So let's just look at this in terms of two students, and this is the social distance game. You have student 1 and you have student 2. And notice here, the payoffs were, if both go, then that's not so great, because they both have a chance of, they sit next to each other and it's pretty close, and they have a chance of, say, catching something from one another. However, if you go and the other person doesn't go, that's ideal. You have the class to yourself. You run lower risk. There's enough distance between you. You get a 4, and the other person gets the other student gets a 1, and that's because they don't go. It's preferable not to go than go and run a risk. And likewise, if you don't go and the other student goes, then they get a 4 and you get 1. And if you both don't go, then that's the same utility of, well, not going, you don't care what the other student does, you still get a 1. Now, there's 2 pure strategy Nash equilibria here, which is the 2 asymmetric ones. And that's one student goes and one student doesn't go. So here, if you choose not to go, the other student chooses to go, you clearly don't want to go because it'll be too crowded, you might catch something. If you're not going, then the other student's going, then of course he doesn't want to not go because he's getting a 4 rather than a 1. And so that's why we have these 2 asymmetric equilibrium. Notice there's also a mixed strategy Nash equilibrium. It's fairly easy to see here is that because not going, you get a payoff of 1, and it doesn't matter. So to be indifferent between not going and going, you need to get the same payoff of 1, which pretty much is if the other student plays not go with probability 1/4 and go with probability 3/4. So in this, you get an expected payoff. 1/4 times 4 is just 1. 3/4 times 0 is 0. So whether you go or not go, you get an expected payoff of 1. So these are the three equilibria in the social distance game with two players. And the equilibria is pretty much what I said: 3/4 go, 1/4 not go, and they all have at least with the mixed equilibria is an expected payoff of 1/1. Now the solution to this is, well, you might want to limit capacity, and what this would do is it would actually aid in coordination. So you say, well, look, we'll have a restaurant, but we'll only see people a certain amount. Or we'll have a performance, we'll only let a certain number of people in. In terms of the tutorials, once, say, 5 students get in the tutorial, that's it. And this limited capacity at least would aid in coordination, because if they're playing 1/4 and 3/4, there's actually a fairly high likelihood that they both might go. And so by limiting capacity, you'll more likely wind up in one of these two squares. So this would help aid in coordination. So the event with externalities is it's the same thing, but the previous game didn't quite take into account what we call externalities. And what I mean by that is, say I live in New York City, I want to go to work and I take the subway. It could be worth the risk to me, but if I get sick, I don't only get myself sick, but I may pass it on to other people. And I'm being selfish, I might not care about this. So I'm not internalizing these externalities. So if we readjust the payoffs of the games just to make it a little bit easier, what this is instead of, say, 1/1 for not go, I increase the payoff of going and not going from 4 to 6 just to make it a little bit easier. And here you can sort of see that if you both don't go, it actually is a better situation for everyone. So here the sum of the two payoffs are 8, and in either these equilibria, if we're alternating between them, then the payoff there is 6 plus 1 or 7. So for society, we want people not to go to these events. But if you allow people to find an equilibrium, then maybe they go to one of these asymmetric ones, maybe a mixed strategy, and we'll get a little bit more attendance there. So the equilibria here are more or less the same. But say the asymmetric equilibrium, we're getting one person to go and one person not going, when actually the optimal level is actually no one goes there. So what we see in the social distance game is that because people aren't internalizing the externalities, that the equilibria has a larger number of people going to work or going to these events than is optimal. It's reduced from everyone going because of this, but it's still not the optimal level. It's not that everyone's going to work. Because of the virus, some people stay home, but given the fact that some people stay home, there's some space for someone to go. And they say, oh, well, it's not so crowded, maybe I go. So one of the solution, well, just telling people of the risks might not be enough, and the government might want to actually impose restrictions on doing certain activities. And actually tonight, just a few minutes ago, the Israeli government said they're going to actually close malls, close coffee shops, close movie theaters. And that's just, they want to actually impose restrictions on doing these. And this makes sense according to game theory. So basically what overall do we learn is that hoarding goods, even those that aren't relevant, like toilet paper, might actually be an equilibrium outcome that's bad for everyone. It's what we would call a self-fulfilling hypothesis. In response to a threat, people will reduce activity, and some coordination may be necessary, and it may be optimal to go with this, go on with this reduced activity. But sometimes the externality is so great that the government actually needs to step in and actually reduce the social distance. So if the externality is small, just let the equilibrium go on. It's not so bad. At least with the two-player game, if it's not too great, the externality, then it would be optimal just in the asymmetric equilibria. But if the externality is too great, the government actually needs to step in and to actually impose laws to reduce social distance. So hopefully you've paying attention to all this news and learning something about the coronavirus. Actually, you can use some of your game theory to better understand the situation. So I'll leave that for now.